So here's our little scheme. What we're going to do is we're going to push the arguments onto the stack. So we're going to use the stack to pass all the arguments in. And what's the advantage of putting the arguments on the stack? Well, we can put as many as we want on, right? We're not going to suddenly run out of registers by saying if they go in registers, you can have at most 26 arguments, and after that, sorry. We can put as many arguments as you want. Okay, and then we're going to, once we have the arguments, and now we start executing in the procedure, you'll see that we're going to put a bunch of other information onto the stack as well. So we're going to save, the first thing the procedure is going to do is to save away the value of the LP register, because it knows that at the end of the procedure it will need it. Why would it save it away? Remember what the problem was in our bogus example early on? If there are any nested procedure calls, they will want to use the linkage pointer as they transfer control to the nested procedure. So in order to free up the linkage pointer for use inside the procedure, we first go ahead and carefully save it away. And some compilers are very optimized out the wazoo, and they notice if there are no nested procedure calls, there's no reason to save the linkage pointer. But we're going to be dumb. We're going to have these little template-based things that know nothing about the insides of the procedure. We're just going to assume we always need to save away the return address because it might be overwritten if there's a nested procedure call. We're going to save away this base of frame pointer. So there's a value that comes in, and you'll see why in just a second. Because the next thing I'm going to do, so I'm carefully building up this picture of a stack, right? So you see a detailed picture on the slide, but if I just think about this, think of this as my stack of books, right? So here's one book, and here's my next book, which is some number of locations on the stack. What I'm going to do is the base of frame pointer is a pointer, if you will, to the current book. And so when I got called, I had a pointer, if you're calling me, the base of frame pointer pointed to your book, your activation record. And what I want to do is when I'm done building my activation record, I want to use the base of frame pointer to point to me. So I save away the pointer to your activation record, and I will restore it before I return to you. Okay, and then finally, there are other things so I've carefully got the arguments here, and then the safe value of LP and BP. And then the other things I'm going to put in here are any temporary and local values that I need. Any registers that I need to save will go on the stack. Those are all the things that appear in a particular activation record. Okay, so you can see that what we're doing, we don't really need the base of frame pointer. It turns out we can do everything off of SP, but it's just convenient for lots of reasons to just have a single pointer that always points to the same location within the book. And we'll see how that works in just a second. So here's our details here. Yes?
So BP, what exactly is that?
BP will be the address of a particular location in the activation record.
Which particular?
Well, I'm about ready to tell you exactly which location it is. Okay, it's this location here. Okay, so the caller will put all the arguments onto the stack. Then I'm going to save away the LP and BP registers. Okay, remember that old BP pointed back to the book from the activation record of the caller. That's the moment. And then we'll set up the BP here in my frame. I'm always going to set up BP to point to exactly that location. The location in the activation record, which is just below where I saved the previous BP. That's just a convention. It could point to other exact locations. The advantage of choosing this one, as we'll see, is that the arguments will be a fixed distance from the base of frame pointer, and all the local variables will also be a fixed distance from the base of frame pointer. So it's just think of it as like a data structure. I have a pointer to the data structure, and I've just happened to set it up to go this way. I really can't change BP until after I've saved the old one. That's sort of the earliest moment I can go ahead and put a new value into BP after I've saved the old value of BP. Okay, the arguments are pushed on in reverse order. Anybody know why I push them on in reverse order? Notice if I call f of 1, 2, 3, 4, first I put 4 on the stack, and then I put 3 on the stack. Why am I putting them on in the reverse order? Yes, sir?
Because your BP is below your arguments, you're going to be going
Right. So, but you can imagine that, at least in theory, arg0 could be first, and the last argument, it would still be a fixed distance away. But you're definitely on the right track. It has sort of to do with a convention I talked about earlier, of passing, variable numbers of arguments. Right. So here, the first argument is always a fixed offset from the base of frame pointer. If I push it on last, it'll always be exactly two words above where the base of frame pointer points. Right? And so if you think about how something like printf works, it's, the first argument gives you all the information you need to know how many other arguments there are going to be. There's a var args, thing you can do in C, which sets up the procedure so you can actually ask the procedure how the procedure can ask how many arguments did I get this time, and all of that really depends on being able to get to the first argument without knowing how many arguments there are altogether, because the first argument will tell you, and if you can't get to the first argument, well, you're sort of screwed. So we put the arguments on in reverse order. Okay, so remember, if you're evaluating the arguments in reverse order, any side effects that happen on the last argument will actually happen before any side effects of evaluating the first argument, something that people sometimes, go, oh, I never knew. So hopefully you're not hiding side effects inside the evaluation of expressions, but sometimes people do crazy things. Okay, so we push them in reverse order so that we can always get at the using a fixed offset from BP, and in fact it's going to be -12 off of BP. Whatever the BP, the address of whatever, the number in BP is the address of this memory location. If I subtract 12 from that, I'll have the address of the first argument. Okay, so in assembly language, if I wrote something like -12, well, if I wrote load BP, comma, -12 into R0, that's going to take the contents of BP, subtract the constant 12 from it to compute. So this is, well, that together, the addition of the value of the BP register and the -12 is that addition, which is what the load instruction does for me, gives me that address, and it's the contents of that address that get loaded into R0. So this would be the assembly language statement I would use to actually get the value of the first argument. And then if there's any local variables, I just use a big allocate statement to leave room for them on the stack, and they'll be at positive offsets. So this is not, you can say, couldn't I have had a different convention? Absolutely, you could. But we need a convention. I'm describing one here. Others are possible. Yes, sir?
So if you can understand everything up until the point with BP,
yep.
Putting it in a certain order that it's put in allows you to have variable numbers.
Oh, so what you want to know is, why does putting the arguments here in reverse order allow me to have a variable number of arguments? The answer is that typically when I have a variable number of arguments, something like the first argument will tell me how many other arguments there are. If I put them in the other way, I wouldn't know where that first argument was, because it would be, I'd have to know how long everybody was. Right? By putting it this way, the first argument is always in the same location relative to BP. And I can look at it and say, oh, now I know how many arguments there are.
What exactly does BP do?
BP is just the address of a particular, it's like, I've got this activation record, it's a data structure. BP is essentially a pointer to our data structure. Right? It lets me go access the arguments and the local variables and the saved values of BP and LP. In that area. So all the the way we'll use BP is always with negative offsets for the arguments and positive offsets for the local variable. But that's how the compiler will access all that activation record information, by making relative accesses to BP. Okay.